The first seminar of the year will be about CARMENES-PLUS, an upgrade of CARMENES and the impact on its science, and will be given by Roberto Varas, who works here at IEA. So Roberto studied aerospace engineering in the Universidad Politécnica de Madrid, and then he made a master on space science and technology in the Universidad del País Vasco. Then he started working in instrumentation, working on a polarimeter for the new robotic telescope in La Palma. Then he got a summer grant to work at the Instituto de Astrofísica Canarias in Tenerife, and after that grant, he came here to IEA to work in the Universidad en the Unidad de Desarrollo Instrumental y Tecnológico, so as mechanical engineer in many different projects, CARMENES, in the Observatory of Nevada too, etc. And since November, he's making a PhD working on CARMENES, studying exoplanets on dwarfs, and the scientific case for Markov, working with Pedro Amado. So we will be talking about CARMENES-PLUS, so the floor is to you.
Thank you very much. Hi everyone, as my presenter said, I'm Roberto Varas, working at the UDIT, and today we'll be talking about CARMENES-PLUS and the upgrade on the cooling system. First of all, I would like to thank you, all my colleagues, Rocío Calvo, Pedro Amado, Santiago Cerreira, and all the Calar Alto staff that has been doing a great job for what I will be presenting today. The outline is as follows. Let's take out this, otherwise you won't see the titles. First, I will be talking about the overview of CARMENES as an instrument, and then about the cooling system of the near-infrared spectrograph description, and then the next step is to talk about CARMENES-PLUS, the project, first the goals, the timeline so far, and the upgrades. And once presented the upgrades, the next step is to talk about the new performance of the near-infrared, the science that we can do with this new stability of the instrument, and working with CARMENES as a visible plus near-infrared instrument. Okay, the chat is. Okay, so first the CARMENES overview. CARMENES means somehow a Calar Alto high resolution search for M dwarfs with X-ray, with near-infrared and optical SL spectrographs, and basically it's all the description of the instrument, placed at the 3.5-meter telescope in Calar Alto, observing with two spectrographs, one in the visible and one in the near-infrared, making radial-velocity measurements with the goal of detecting exoplanets around late-type main sequence stars in the habitable zone. And the observation started in 2016 and was planned to work until 2020, and then CARMENES-PLUS came to extend and to improve the performance of the instrument. Here we have a table with all the basic parameters of the instrument, but let's see some cool images. Here we have the 3.5-meter telescope, very impressive. But if we see on the right a zoom of what is the category in focus, there's a black cylinder with the logo of CARMENES, because that is what we call the front end. All the light comes from the telescope to that point, and some fibers takes the light just below this technical floor, like we can see here, where the spectrographs are. Here we have an image of the a view of the instrument on the clean room of the UDIT with all the stuff that actually make this possible. The big cylinder on the upper part is the outer layer of the spectrograph. That is what we call the vacuum chamber. That is the first layer that allows us to be under vacuum conditions. The next layer is this, the radiation shield. Okay, and if we remove this layer, we have the optical bench with all the optics. That is the actual spectrograph itself. Okay, so that's from the overview of CARMENES, and now the cooling system of the near-infrared channel, because we're looking at the near-infrared. We want to work at approximately 140 Ks. So we need a lot of stuff to make this possible, and the cooling system has, as I said, a lot of layers. The first one is the vacuum chamber, that is here is almost invisible. That basically allows us to be under vacuum conditions, so the convection and the heat load of the air is almost eliminated. The next layer is the radiation shield, that by definition minimizes the heat load coming from the radiation, but here in Carmenes makes another huge role, that is basically to cool down the system. Okay, as I said, we want to work under cryogenic conditions. We actively cool down the radiation shield with these purple boxes that we can see attached to the radiation shield. Is what we call the heat exchangers on the top. And I want you to keep in mind this because it will be very important to understand how it works. And then inside of this, we have the optical beds. That is the part that we actually want to cool down. Okay. I hope that this doesn't disturb us anymore. But okay. So these are the layers of the spectrograph. Okay, and the cooling system, that is the part that concerns us, is with a easy sketch that we can see here. The first step is the blue bottle on the bottom with the number 1. That is where the liquid nitrogen is inside what we call a dewar or a tank of 350 liters. This gives us liquid nitrogen to the orange part. That is the next step, what we call the nitrogen gas preparation unit, or to be shorter, preparation unit, that basically evaporates the liquid nitrogen and give us a very stable flow of gas. Because this is what we are going to use to cool down the system. Then through the exits, we go to the inside of the instrument. And just before reaching the radiation shield, what we have is the flow splitters. The flow splitters basically split the flows. So we have a lot of different circuits of gas that goes to different parts of the spectrograph, to these small boxes that I told you before, that are the heat exchangers. That is where actually the heat exchange between the radiation shield and the gas happens. And then all the lights come together again and to the exit of the instrument. And just before going to the atmosphere, we have what we call the on-off valve that basically allows us to control the flow. Okay, this is also a very important part of the system. It has only 2 states, open and closed. When it's closed, the flow remains, or the gas remains inside the instrument, exchanging heat with the radiation shield. And when we open it, the gas refreshes on the lines, coming with new cool gas. Okay, so the working mode here is opening and closing the valve all the time. And with a PAD, an automatic method, what we do is to keep the temperature as stable as possible. And just one last thing about this, and is that the bottle at the beginning, where the liquid nitrogen is, every morning is exchanged because we run out of liquid, so we place a new bottle. This also will play a huge role on the system. Here's just a 3D model of the cooling system, that is with the preparation unit on the left. Then the gas comes to the system. We here can see the flow splitters, and then the small boxes that are the heat exchangers, and then also the vacuum vessel and the radiation shield. So this is for the description of the cooling system. Okay, now let's talk about CARMENES-PLUS. This is a big and a huge project that involves all the instruments, the visible spectrograph, the near-infrared spectrograph, the calibration unit, the pipeline, everything. But in this case, we're talking just about the cooling system and the near-infrared. So we have 2 main goals. The first one is to improve the stability of the temperature on the instrument, so we have the capability to do more ambitious science. And the second one is to reduce the maintenance tasks that are needed to keep Carmenes working every day. The timeline is summarized somehow in this chaotic line. Okay, a lot of things happened starting in 2020, as I told you, when Carmenes was supposed to end. CARMENES-PLUS starts. We have the COVID, we have a lot of things. Okay, but I want you to keep in mind just a few of them. The first one is February 2021, when we discovered that the preparation unit was broken and we don't have the capability of evaporating the liquid nitrogen. It wasn't until May that there was an inspection that discovers that the heaters were broken, the heaters that allows us to evaporate the gas. Okay, at the same time, we placed what we call a proportional valve. Remember that I told you we were working with an on-off valve. Basically, when you're working with an on-off valve, we have what we call discontinuous flow, because we are opening and closing, no other states in between. But with a proportional valve, we have as many states as we want between 0 and 1. So we have a continuous flow. Then on September of the same year, 2021, the preparation unit was repaired. And again, we have the capability of evaporating the gas. And the last date that I want you to keep in mind is the end of May, beginning of June of the past year, 2022, when we made the last or the biggest upgrade of all of them that I will be explaining, so don't worry. And it's called Fixed Dwarf. Okay, this is the end of May 2022. Here we can see the broken heaters. We have on the right an image showing they are basically resistors that are broken, so we cannot evaporate anything. There's also an interesting image on the left that is showing the inside of the preparation unit. This is the first heat exchanger that is in charge of evaporating the liquid nitrogen. Then we have different stages that keeps the flow very stable before exiting the system. And now we have this, the preparation unit repaired. On the left, the same disk as before, but outside of the preparation unit, and the test that we performed to see that everything was going fine. That's for the milestones so far. Now let's talk about the upgrades. The first one is the one that I told you about, the continuous and discontinuous flow mode. We basically install in parallel to the on-off valve at the proportional one, in parallel, because we wanted to always have a backup in case that it doesn't work as we planned. So it starts working on a continuous flow. Here on the bottom, on the left, we have an image showing how it works with the on-off valve. On red, it is the state of the valve that is going back and forth, opening and closing all the time, as I told you. And the temperature in black that is following this behavior, going back and forth, back and forth. So we can see this is a source of instabilities. That's why we choose to go to a continuous flow mode. And basically the difference is very easy to understand. We in red have the discontinuous mode flow, going back and forth, and in blue, when the continuous flow was performed, very stable. So the first improvement with this upgrade is very noticeable. The next one is what we call the automatic system, vacuum system for transfer lines. But first, I want to explain a little bit why we had to implement this upgrade. We basically have vacuum conditions on the system, okay? And if you perform vacuum on an instrument or in a system and you let it go without doing anything at all, we lose these vacuum conditions over time. We have a degradation of the vacuum. So when the vacuum is lost, we have a bigger heat load coming from the convection, so the temperatures start to rise about a rate of 1 K per month until we decide that this is too much. So we do what we call a vacuum pre-generation. We basically do again vacuum to keep the pressure under the levels that we wanted. And this has also a huge impact as this thermal jump. So here about 13 Ks that we want to avoid, because as I told you, the main goal is to have a long and short-term stability of the instrument. So basically, to avoid this long-term thermal drift and the thermal jumps, we install this system, automatic vacuum system, that keeps the pressure very stable around 10 to the minus 7 millibars. Okay, and just to show you very easy at a glance how this works, we have two differences on the left before installing and on the right after installing it. There's two differences. The first one is that on the right now, there's a lot of stuff in the same spot. It's very crowded that before it didn't have. But in exchange, we lose this formation of ice that is surrounded by a red circle. That is basically a sign of the lost vacuum. Okay. The next step was to implement a pressure control unit. First, I will tell you how these problems happen to need a pressure control unit. This is the bottle tank where the liquid nitrogen is that I told you at the beginning, that is at the very beginning of the cooling system. Basically, it's a bottle with some amount of liquid, but on the top we have gas, nitrogen in gas phase, that keep us with some pressure, some overpressure over the atmosphere. depending on this pressure, the amount of liquid nitrogen that goes to the system changes. So this is basically how we can extract the liquid from the bottle with the overpressure. But there's some sources of instability that change this pressure. For example, the exchange of bottle every day, or the lower of the level. We have when the liquid is lowering, the gas volume is increasing, so the pressure lowers. In order to avoid this source of instability, because we have what we want is a very stable flow of gas to the system. If we have changes on the flow, we have not this condition. We install what we call the pressure control unit. That basically is in charge of keeping the pressure around 0.41 and 0.42 bars over the atmosphere. It has two working modes. The first one is when the pressure is too high, we basically exhaust the gas to the atmosphere, and when it's too low, we inject gas with this secondary bottle that is called the buffer dewar to the system to keep the pressure in between. We don't do it manually, it's basically automatic. And the difference is very huge. On the left, again, animals showing the pressure, on red before placing this PCU, with a lot of changes of temperature, of pressure, sorry, every day and every night. And in black, we have these very, very small changes of the pressure. So this is also a very huge improvement in terms of stability. Again, more things going on in the same room. It's getting very crowded. You can see here the bottle that is feeding the system and the PCU. And finally, the biggest upgrade that I told you that happened at the end of May 2022. Well, this arises from a fact that I didn't explain yet, that is a bad side of the exchange of bottle. Okay, every morning we run out of liquid nitrogen, so we want to take out this bottle and put a new one. In the time in between, we take the first out and we place the second one. We are not taking liquid nitrogen to the system, so we are basically not cooling down. There's a small time that basically there's no liquid nitrogen. So this is also a huge source of instability for the temperature, as we are going to see very soon with some images. So the solution was basically to design what we call the fixed dewar, that is one bottle that is always filling with liquid nitrogen, and when the fuel or the liquid is too low, the level, we refill the same bottle with a secondary one that is here in orange. Every morning we put this second bottle full of liquid nitrogen towards the other one, open the valve, and basically refill the other one. So there's always a flow to the system of liquid nitrogen. There's still some small instabilities for this process because it's very chaotic in the reality, because thermodynamics are always very exhausting. But the PCU plays a really huge role on keeping the pressure inside the bottle very stable, to have a very stable also flow to the system. Again, more stuff on the same room, very crowded now. And the temperature image that I want to show you. In red, we have previously this upgrade, previously refilling the bottle when we replaced every morning this dewar. And we can see that every day there's a huge jump on the temperature, that basically is resetting the system every day. And this reflects directly on the radial-velocity measurements. And after we implement this fixed dewar, we have the blue line that is quite more stable. We have still some instabilities, but it's in another league, let's say, okay? But ultimately, what we want to do is to make radial velocity measurements. So how this translates to the radial velocity. Before going to the graphic, I want you to explain what we call the nightly drift of the radial velocity. It's an easy concept, but I think it should be explained. Every night, what we do is some calibrations of the night to see how the instrument is performing, radial velocity calibrations. And the first one, we set it to 0. So the rest of the calibrations done in the night are referred to this first one, okay? we do this every night. The first one is 0, and the rest are referred to this one. We want to be this drift, that is all the radial velocity calibration measurements all together. We want it to be as small as possible because we want to make very accuracy and very stable measurements. So this should be as close as 0 as possible. And here we can see the impact of this last upgrade. The black line represents the end of May 2022, sorry, when we implemented this new configuration. So on the left, we have the system with all the upgrades except this last one, and on the right, all together. And the difference is huge. Okay, we basically have this nightly drift that is quite smaller now than before. So the improvement is quite noticeable. Okay, then we are going to talk about the numbers, so it will be easier to understand all of this. And just to finish with the upgrades, I want to talk about the future work that is even ongoing, some of them, as they're refilling every 2 days instead of 1 day. We just put a little bit more of liquid nitrogen, and the system is able to be even 2 days working with the same bottle. So this impact on the refill is every 2 days instead of every day. So this is also an improvement on the long-term stability. We want to make this process also very automatic, because right now it's mostly manually, the open of the valve and so on, and it's very demanding from the Calar Alto staff, and also it's less optimized. What is also going on, it's the migration of the control system to a more powerful PLC, so it is easier and basically better control of the proportional valve and all of the system itself. And finally, in case that this is not enough for fulfilling the requirements, what we have is a new preparation unit called the Evolution, or the EVO, and a preliminary design is shown on the right. And the next step is to talk about the performance. Explain all the upgrades, what is the result on the instrument. First, we're going to talk about these calibrations, these nightly drifts, okay, that is basically what is shown on the left. We're going to be comparing the pre-CARMENES-PLUS era to the post-CARMENES-PLUS. Pre-CARMENES-PLUS is just until February 2021, when the preparation unit broke, and always with the on-off valve, so with the discontinuous mode flow. And on blue, we are going to explain the post-CARMENES-PLUS, that is after this last upgrade on May 2022. So we have the calibrations and the nightly drift for every night, but these are just graphics, as we can see on the top for the pre-CARMENES-PLUS, in the bottom after CARMENES-PLUS. Just to notice that on top we have this behavior that is going back and forth, back and forth, back and forth of the radial velocity. That is just what happens with the temperature. That's why we want a very stability of the temperature on the system, because it is directly reflected on the measurements. And to represent these graphics, to have some numbers, we took two values. Okay, the first one is the peak to peak, the maximum difference during the night, because we want it to be as small as possible. So this is a reflect of how small the radial velocity, or how big the radial velocity drift is. And the second one is chosen because we also want to be the radial velocity drift very smooth, because we can do some calibrations and some corrections to the results if we have these values. But if it is very erratic, as it is on the top, the corrections are going to be not very useful. But if it is smooth, as in the bottom, the values are going to be, or the corrections are going to be very valuable for us. And the smoothness, we measure it via the root mean square value. That is basically, first we do a quadratic fitting to the data, that is the black line shown in the figures. And to the residuals of this fitting, we make this root mean square method. And that is the second value representing every night. Okay, so we have the peak to peak value, that is the maximum difference, how big the drift is, and the root mean square value, that is how smooth the drift is during the night. And because we have a lot of data, a lot of nights, we're going to do a statistical analysis on the left for the peak to peak, on the right for the root mean square, in blue, the post-CARMENES-PLUS, and in red, the pre-CARMENES-PLUS. And at the top, we placed the median of the distribution, and it's easy to notice that the improvement is very huge. We come from 30 meters per second to just 17, almost a factor of 2. And it's even bigger on the root mean square when we come from 4.7 meters per second to just 1.6. So now the drift every night is smaller and smoother. And we see the distribution is also quite better because it's more to the left and higher. So we have more common lower values. So also the long-term stability has improved. Nevertheless, we should keep in mind that we are comparing years of data, previously CARMENES-PLUS, with months of data after CARMENES-PLUS. So we need to keep recollecting this data to see if this is actually the reality of it isn't. And the second step is to compare with the visible spectrum. Why with the visible spectrum? Because it is quite better, the performance is quite better for all the history of the instrument. So we set this as a reference. We want to be at the precision that the visible has on the radial-velocity. So we do exactly the same analysis than before. Here in green, we saw the visible results. And what we can see on the top with the medians is that we're very close to be at the visible performance, but we're not yet at the same level. Okay? So we hope that with the new upgrades and the optimization that I explained, with the future work, we can be even closer to this performance of the instrument. So this is all the analysis for the intrinsic performance of the instrument. Only talk about calibrations, how the instrument works itself. Now we're going to see how it performs on sky, if there is any improvement when looking at standard stars. Because in CARMENES we have 6 standard stars. So here in the graphics, that are observed very easily and selected because they change. They don't change a lot over time, so the measurements should be very stable. On the left, we have basically the number of observations that we have for each standard star. There are plenty more of them on the pre-CARMENES-PLUS era, basically because there's years of data and now just several months. But with a little bit more of data, we can see if this is also the reality of something is changing. Maybe we have even a bias. But for the moment, what we do is to take all the observations for each star and each color, okay, pre and post CARMENES-PLUS, and we do the root mean square value of all the measurements and the standard deviation of the errors. And what we plot is on the right, the value of the root mean square of all the observations, and the error bars are the standard deviation of the errors of each measurement. And what we basically can see is that just with one exception, that is BD plus 112567, is that the errors are quite smaller. The values are also smaller, but the errors are very, very much lower than previously CARMENES-PLUS. And it is also shown on the distribution on the Instagram of the errors. Okay, we can see that they are more concentrated around a lower value. On the left, we have pre-CARMENES-PLUS, and on the right, we have post-CARMENES-PLUS. And it's very obvious that with just the exception of the red line, that is the same as before, all the values are concentrating around a lower value. So this is also a huge improvement when comparing the near-infrared before and after CARMENES-PLUS. But what happens when we compare again with the visible? Okay, we didn't make a lot of observations in this sense, a lot of studies, but first we know for sure there is a fact that there's more information on the spectrum on the visible bandwidth than it is on the near-infrared. But in case they both had the same information, because the instrument is performing very close to the visible level, the signs that we can do should be very similar from the visible than from the near-infrared. Nevertheless, this should be tested because we also have the front end, the fibers, the mirror of the telescope that are basically optimized for the visible, and also the effects of the atmosphere and the star variability that for sure are different from the near-infrared than from the visible. So this can limit our accuracy in both spectrums. But there's good news, because if we go to the latest spectral types from M6 to M9, what we can see is that the signal to noise ratio is almost at the same level for both parts of the spectrum. Basically, even though we have more information on the visible, the stars emit more on the near infrared because they are cooler. And if we go to latest spectral types, M8 and M9, the radial velocity precision in theory is even better for the near infrared. So this is good news, because if we have a very stable near infrared spectrograph, we can actually go to this limit, performing even better than the visible. So that's why we want to work with CARMENES as a visible plus near infrared spectrograph, because until now, this wasn't a reality, okay? We could do a lot of science with near infrared before, but now with the new stability, this is going to improve for sure. And there are plenty of interesting cases scientifically. The first three, I put just 5 bullets of interesting cases. The first 3 ones are basically about the chromaticity, because if we do chromaticity analysis on the radial velocity, we can compare the stellar activity with the amplitudes of the radial velocity on both parts of the spectrum and talk about the disputed planets. This is the case, for example, as the co-rotating planets, such as AD Leo, where the near infrared can play a huge role in deciding and reinvestigating these cases. Also, the chromatic Rossetier-McLaughlin analysis that basically give us a lot of information about the orbital parameters of the planet, and also the velocity that the spin of the star is. And with a more stability and more stable near infrared, we can go to smaller values and to more critical cases. And also not only the chromaticity, but also the atmospheres will benefit from more stable analysis. Also, the telluric removal should be quite better, and we have also the case of going to cooler and cooler stars and detect exoplanets around these ones. I want to extend a little bit just this last point about the ultra-cool dwarfs and brown dwarfs, because there's a lot of stuff going on there that we don't know, because we see a trend on the latest spectral types that the number of exoplanets detected is going higher and higher on small exoplanets, and we want to know if this is also true for the coolest stars for the brown dwarfs, that there's no population known about exoplanets on brown dwarfs. So it's also very interesting. And in the case of transiting planets around cool dwarfs and ultra cool dwarfs, the atmospheric analysis again will benefit for this analysis, because they are best cases for analyzing the atmosphere that the hottest stars. And just as a last point, the problems that we have when looking at ultra cool dwarfs and brown dwarfs, basically the models are unconstrained because there are not a lot of detections. We also know that they are very fast rotators, and there's just few things that we can do about this, and it's just to select the slowest ones. And finally, we know that they are faint. So this is why basically there's no a survey about these exoplanets around ultra cool dwarfs, but there's some things that we can do about the faintness of the stars, and it's going to bigger telescopes. And that's where Marcot comes to play. There is a project going on between the IAA and the Calar Alto staff, and it's basically to go to a 15-meter telescope, so we can even connect CARMENES to this telescope and have a bigger surface, so we have a better signal to noise ratio, and all these problems that we are seeing here are going to be less important. And this is the conclusions summary, that the Zoom doesn't allow us to see that they are the conclusions, but we basically talk about the cooling system and then all the upgrades. The first part of the analysis of the results was to see the intrinsic performance of the instrument, and was easy to see that it was performing quite better than before. but we are not yet at the level of the visible. That is our goal, basically, to go to the same level of the visible. Then we talk about on-sky measurements. We need more data of standard stars, and especially on the latest spectral types, because we want to go to ultracool dwarfs, but we don't have actually standard stars on latest than M2. I think is the latest one on the standard stars, and we are planning to implement some standard stars around M6 and M7 or even later if we can. And finally, the ultimate goal is to see the capability of the instrument right now, and with the future upgrades that we are planning, have we reached the theoretical performance, which is the actual accuracy, which is the limit now, and all this stuff, basically. If how are we performing, and which are the cases that we can reach with the level, because we want to use CARMENES finally as a visible plus near-infrared instrument, and do this chromatic analysis that I explained, and also to see the atmosphere of the planets, even on the latest spectral types. So that's basically my presentation. If you have any question, I will be pleased to answer them. So thank you very much.
Thank you very much, Roberto, for this talk. And as you say, if anybody has questions, please raise your hand. And Francisco in the room can manage it.
Okay, Roberto. First of all, congratulations to you and all your team, because it's a great job. And I say this because I'm not sure if the scientists know how difficult this is to achieve this precision and stabilities in temperature and in flow control and finally in the radial velocity. So it's a great job. So and in one of your first slides, you said that the goal was 2 meters per second in radial velocities in the long term, and 1 meter per second in the short term, I think. In the conclusions you said, I'm not sure if I got that. You don't know how what these numbers are in the pre-CARMENES-PLUS configuration now. The near channel, you don't know which is the radial velocity precision or
This is a tricky question. Okay, I will explain it for sure. What's in my hand, because there are several ways to compute a number to see which is the intrinsic performance. Okay, but it depends on how you compute it actually, or you calculate it. The number changes. So we have numbers from before CARMENES-PLUS showing a certain number. That is probably what this refers to, because there's a lot of people also working on this, so it's quite difficult to understand what they refer exactly. But basically, they compute a different analysis than this one I show you today. So we decided to take another way to compute it, because we also use the data that we had in our hand, and that's why I do the same analysis for the visible that for the infrared before and after CARMENES-PLUS, and the numbers are not referred to these same numbers. That's something that we are working on it. We want to have this number precisely. The 2 meters per second is not possible to compute it actually, because it's over 5 years. So we need to see if this is actually happening. The 1 meter per second is easiest, because it should be in the short term, I mean days. And this is something that we can actually compute, and we are actually trying to do it, because we have 2 fibers. One is that on sky that we call the fiber A, and we also have the fiber B, that is the one that makes the calibrations. It also changes a little bit when we are observing with CARMENES, that when we are not observing with CARMENES, these values, these drifts, and the calibrations changes a little bit. So it's quite tricky to fully be sure that we are doing the best way to compute these numbers. So I'm sorry, because I'm probably not answering the question actually, but that's what we do at the moment. I hope I can give this number very soon.
Okay.
Thank you for the question.
Thanks, Roberto. I enjoyed the talk, which I didn't think before I came. I said, oh, it's a technical talk. It's horrible number. I really enjoyed it.
Thank you very much.
Very naive question, because I have absolutely no ideas for that. Why do you have to evaporate with nitrogen? And is the gas flow, is it just too difficult to handle liquid nitrogen, or is it more stable with the gas flow? What is the reason to evaporate the gas?
It is also quite a tricky question, but thank you very much again. Okay, it's because the team just selected that the working temperature will be 140 Ks. And in case you work with liquid nitrogen, you are working at lower temperatures. Basically, that is the concept. Okay. It is also because ISO participates on the design of this cooling system and wanted to try the same concept that is used for the detectors, but they wanted to make sure that it happens also with the instrument that works well. In the end, it was quite harder than for just the detectors. But basically, it's because of that, because of the working temperature. Other instruments use liquid nitrogen for the detectors, also for all the instrument, but because they are working at lower temperatures.
First of all, I would like also to congratulate you on the very impressive results that the upgrade is very good. I would like you to mention a little bit about your contribution to the upgrade, because it was not clear to me which was your contribution.
Okay, thank you very much, Fran, for the question. In case from Zoom you didn't hear, is basically what is my contribution to this work, myself. Yeah, I didn't explain actually because most of the work is not mine. Okay, until 2022, basically the beginning or the end of 2021, I didn't start working at the AIA. So all the work, let's go to the upgrades. That is basically all the timeline until this moment. Nothing is for myself. Okay, but Rocío here did a lot of work. The automatic vacuum system that refreshed the line and the vacuum was from her side, but for my side. Okay, I basically participate on the design of the preparation control unit. We basically do it here at the Rocío and I, and then also with the Calar Alto staff, we just do the, let's say, the theoretical part, because they implement all the upgrades and do all the manual stuff. We have a really strong campaign also on the fixed DWAR when we were refilling the process. I also participate strongly on this upgrade. We go several times to the observatory trying to see if this works, and it took us several months until it worked well, because it looks very easy to refill just a bottle, but it's really hard because a lot of things are going on when you're doing this. And finally, I think my strongest contribution is all the analysis of the temperature and all the statistical analysis of the radial-velocities. Okay, all these plots are also all the team, Rocío, and even in Calar Alto, Pedro, Santiago Becerril, everybody participate. Okay, on this. It's not only me, but it's one main task was to analyze all this data, and also the on-sky measurements with the standard stars is basically most my part. Okay, but it's always a teamwork effort for sure. Thank you very much, Fran. Yeah, you want to chat?
Stay on the slide. Congratulations. I have to speak. Okay. One of the questions is a curiosity. You said that you showed improvement in the error velocity for all the cases except it's one exception. That one. Do you know why? Because the night is terrible because the planet is doesn't start?
I don't know why. That's the short answer. Yeah, the question was basically that if we know why we have this exception, the exception on BD plus 11, 25, 67, 66, 76, sorry. On the middle, why this is the exception on the error bars. We don't know why, because we didn't look very much at this data. We want to have more data to analyze it. Because if you see the number of observations on this star is very low. On the 3 latest, we have more observations, so it's we can trust more this analysis, but it's something that we need to work on it.
Kind of inspection of the stars, you have even less observation.
Yeah,
More errors.
it could be the same. It could be also that it's just a bias, or we don't know for sure. The answer, the truth is, I don't know. I don't know, but I want to know it, so I will look.
My main
to
question
it.
was another one, just
Okay.
One of the conclusions, you say something, it's just for me to understand.
Yeah, okay.
But probably you explained, but I didn't understand very well. You say like that one.
Wait, sorry.
Yeah, ultracool dwarfs synthetic planets are small and constrained models. The models you are referring there are planet formation models?
Yeah,
Okay.
the planet formation models.
Okay.
Yeah, there's also a little bit of this here, like, does the population trend of small exoplanets extending to the UCD? Does the observed occurrence rate of Earth-sized planets continue? Digs from planets as efficient as, and also the migration and the impact on the dependence on the star, because the models here are unconstrained, basically
But we can,
the planet formation.
we can say that most of the planets are smaller than what?
Yeah, but the trend that we refer here is that they increase the number of planets. If we go to, it happens before the M dwarfs also, that it increase the number of exoplanets that we detect on the latest one, on the smallest one, the smallest ones. So we want to know if we actually in the brown dwarfs we will have more exoplanets than on the M dwarfs or not. Thank you. We also have a question on the chat, okay? But
Okay, let's start with the
Okay.
Can I see
Sorry.
the new concept of the preparation unit, the EVO?
yeah, for sure. It is very preliminary, okay? Because it's not decided if we need this or not. But yeah, you can make any question for sure. I've never known. Sorry. Not sure. Yeah.
What's the difference or the idea in this concept? You have also 3 installation, 3 stages? Or?
Yeah, the main difference or the biggest difference is that in this case the preparation unit is in vertical. You probably didn't notice, but before we have a horizontal preparation unit, and what we want to achieve with this is that in case we don't evaporate all the liquid nitrogen, all the liquid goes to the bottom, so the gas can flow. Because sometimes we had problems with the actual preparation unit because a lot of liquid stuck on the stage and the gas didn't flow very well. So this is the biggest upgrade, but there's a lot of difference because all the things that we have learned since the beginning of the instrument. We also want to change the spot where the liquid or where the heaters are to evaporate the gas. We want to be on the bottom of this geometry. We also want to be this conic shape because in case also there is some water inside the system, it can form small ice on inside the circuit, and this can also stuck and the gas is not allowed to flow. So if we have this shape, probably it's going to happen here, the ice, so it's not a problem. We also want to have liquid inside the preparation unit before you go inside of the preparation unit and evaporate it immediately, let's say. And now we want to have this first stage that is in blue is going to have amount of liquid nitrogen. So we always have liquid nitrogen inside the system, and the refill is happening inside the system and not outside. So it's also an important part, always having liquid here and evaporate from the surface.
Is it a real plant? Or, I mean, is there money for it?
It is supposed to be money. The problem is that if it is worth it to spend that money on this or not, because they also want to upgrade the calibration unit, and we saw that the improvement already is very huge. So maybe it's worth it to spend this money in the calibration unit better than on this. So it's only in case of necessity to take this plan. Is Pedro Amado asking a question on the chat? I don't know if you want me to read it.
Yeah.
Carlos asked, I think CARMENES is already a visible plus near-infrared instrument, maybe not yet for planetary studies and accurate radial-velocity measurement, but for higher resolution spectroscopy, it works quite well. Maybe the reduction pipeline should improve as well, providing data to the final user in more user-friendly format. Thanks. And Pedro Amado basically responded that is true. Maybe I exaggerated a little bit because I wanted to make a point, and is that we need to improve the instrument, and we're on the path. But it's true that CARMENES is quite successful in the field. It's a reference both in the visible and the near-infrared, because there are few cases that works as well as CARMENES. And Pedro says that even for planetary studies, but we are trying to detect the smallest, more challenging planets, or as the ultracool dwarfs and working with the visible. Yeah, so yeah, but basically I exaggerated a little bit for sure. We have a visible plus near-infrared instrument, but we want to go even further. So actually have same level instruments, because we also have a problem on the infrared that is not from the instrument, but it's from the stars itself. We have less information, and we have, when looking at the, not latest, but the earliest spectral types, we have less information on the infrared, and we're limited by the sky and not by the performance of the instrument. So yeah, CARMENES is a reference, and I not the one that is going to deny this. But my point is basically that we want to go farther and farther on this and take the most out of CARMENES, because we think it is possible. So thank you for the question. There's another question.
How often do you break the calibration? What changes the strategy? What changes the number of calculations?
Thank you for the question. He asked about how it's going to affect the calibration unit upgrade that I just mentioned. Okay, basically the idea is to change how it actually works, not the strategy of observing, but right now what we have is a mirror that is dividing the light into several into the instrument or the calibration unit, and what they want to have is with the fibers to have a fiber, what we call a fiber switch, that is basically easier to change from one mode to another, is fastest, and also these changes that I just mentioned about that there is different result when you are observing with CARMENES than when you are not. We don't have these moving parts, so it's basically the mechanics more than the strategy of observing. And there is even a more ambitious plan that involves also changing the plan, because they want to have a more complex calibration unit with a lot more of modes, of working modes, to have simultaneously the fiber A and the fiber B and not need to switch. So it's basically how it works actually, more than the strategy of how many calibrations or which stars or which lamps are we using. I hope this answers the question. But this is a work that is going on. If you are interested, I can send you the info that we have already. That is not a lot, because it's at the very beginning stage of the project. Thank you for the question.
Are there any questions in room? In Zoom?
There is a question here at Zoom. Pedro, please.
Yeah, hello. Hi, Roberto. Thanks for the talk. I had to join a little bit later because I had a telephone, so I couldn't hear the first part of your talk, but I think I know what you said. More than a question, this is a comment or a couple of comments. First, on this slide that you already have on the screen, for the preparation unit EVO design. I want to say that regarding what you said about the question on when this could be implemented or if it's going to be implemented, there is, I think, one critical point, and that is that the grapes that we are currently performing are trying and are stabilizing the instrument, but we still don't know and cannot evaluate how robust these solutions are. I mean, how well we can keep the stability in the long term. That is our final objective. So if this was not possible because the solutions now were not robust, I think CARMENES, the evolution design would help us with that. And in the end, if this happens, it will be needed to provide a more robust solution to the stabilization that in the end goes with the stabilization of the liquid nitrogen, the liquid gas that flows within the spectrograph to stabilize thermally the instrument. So this is was one of the comments I wanted to make. The other one was related to the other question about the calibration unit. We are also looking into the possibility of building a new Fabry-Perot that is going to be more stable than the one we have right now. This was one of the first Fabry-Perot that the team in Göttingen built for any instrument. This was the first attempt to their design of Fabry-Perot, and it was installed in CARMENES, and they have learned quite a lot since then. They have built few more Fabry-Perot for other instruments, and they want to apply all this knowledge to this new design that will be installed in CARMENES. We can take advantage of this better stability for the calibration light, and also these two teams around the world have contacted us to use CARMENES near-infrared to make tests of their laser com solutions for these calibration lights, because there are no other instrument in the world that provides the stability in the near-infrared that CARMENES gives. So they cannot carry out this kind of test in anywhere observationally on the sky, but with CARMENES. So this is another possibility, that if those tests are successful and we can manage to raise the funds, we may at some point think about purchasing one of these laser com solutions for CARMENES in the future.
Okay, thank you, Pedro, for the comments.
Further questions in Zoom? René?
No more questions. I think we can close.
So yeah, so let's thank